Welcome everybody to chapter 14. How you all doing? Today we will be looking at the topic correlation and linear regression. This is a very important topic in statistics. So our learning objective today is that by the end of this video, you will be able to examine the linear relationship between two variables. You'll also know how to interpret a simple linear regression model. So the things we'll look at is how to calculate and interpret the correlation between two variables. So far, we've been looking at just one single variable. Now, we'll look at a situation whereby we have two quantitative variables and we want to look at their linear relationships. We'll also want to determine whether the correlation between two quantitative variables is significant. And then we'll learn how to calculate the simple linear regression equation for a set of data and know the basic assumptions behind regression analysis. And one other thing we'll look at is how to determine whether a regression model is significant. And finally, we'll explore how to recognize regression analysis applications for purposes of prediction. All right, let's move on. So here is an interesting scatter plot. By scatter plot, we mean that you have one quantitative variable in the horizontal axis and another quantitative variable in the vertical axis. This graph is from a study that examined the relationship between a country's level of chocolate consumption and the total number of Nobel laureates per capita. A surprising strong correlation of 0.791 was found between chocolate intake per capita and the number of Nobel laureates in various countries. So we have it here. And we use the symbol R to represent the correlation coefficient. As you've all seen in statistics, we use symbols to represent different concepts. And it's very important we understand the symbols because with that, it's easy to explain things in a much more simplified way. I know in this course, you all have explored different symbols from expert to mu to sigma and all that, and it can really get so confusing. But the more you familiarize yourself with the symbols, the easier it becomes to remember. Take, for example, if you are doing yoga, you need to constantly practice every single day for your whole body to get in tune. It's the same way with any course you're taking. You really need to familiarize yourself with the concept so that it makes sense to you. Now, if you look at this, up here we have Switzerland. So Switzerland was the top performer in terms of both the number of Nobel laureates and chocolate consumption. So perhaps we need to really eat chocolate and live in Switzerland to become Nobel laureates. Well, as we would see, that something is really correlated does not mean that it implies causation. Now, a correlation between both variables does not prove causation, but indicates that either one variable influences the other, or the other influences the other, or both are influenced by a common underlying mechanism that leads to that correlation. Great. So the sample mean and sample standard deviation describe the distribution of a quantitative variable. That we have explored how to find the sample mean, sample standard deviation. So remember, for sample mean it's X bar, sample standard deviation is S we use. Correlation, however, can be used to describe how two quantitative variables relate to each other. So the key word to remember here is quantitative variables. So correlation summarizes how strong the linear relationship between two variables is. So it summarizes how strong the linear relationship between two quantitative variables. And one keyword here is linear, which means that there could be a relationship between two variables, but if it's not linear, then we would not be compute, there will be no correlation. So correlation summarizes how strong the linear relationship is between two variables. Great. Let's look at an example here. So here's the data of a cruise ship data, which was opened in Minitab. And this data has about 158 records, so the rows. And there are several features of variables of interest. So some of the variables include the crew size, the age, tonnage, passengers, length, and so on. Now, the data is this data will be provided for you in the course, so you can use it to explore the relationship between the various quantitative variables. So when you look at the variables, you can see clearly that age is quantitative, tonnage is quantitative, passenger, and so on. But if you look at this, you can see that it's not, because you have this T, remember, the same thing with this. So that is a categorical variable. All right. So the best way to look at the relationship between two variables is to create a scatter plot, as you saw earlier. So a scatter plot is a two-dimensional plot showing the values for the joint occurrences of two quantitative variables. So in this scatter plot, we're looking at the relationship between number of crew and number of passengers. And as we can see, there seems to be a linear relationship. And by linear, it means that I can draw a linear line between these data points. So the scatter plot may be used to graphically represent the relationship between two variables. It is also known as a scatter diagram. So this is a scatter plot. Cool. Now, how do we describe a scatter plot? A scatter plot illustrates a positive linear relationship. So this is positive. If it's negative, then it means as one variable increases, the other variable decreases. So as this increases, this decreases, so this will be negative. However, this is positive, this is negative. All right, so, and how can we quantify this? So correlation is the degree to which two quantitative variables are linearly related. So when we have a positive correlation, it means that as one goes up, the other goes up. A negative correlation means that both variables don't go in the same direction. So as one goes up, the other tends to go down. So correlation coefficients values are between -1 and +1. If the correlation between two variables is equals to 1, it means that it has a perfect positive linear correlation. If it's -1, it means that it has a perfect negative linear correlation. If it's equals to 0, it means that there is no linear correlation. And if it's in between, I will show you how to interpret it very soon. Okay, so let's look at some examples here. I would like you to guess the correlation of this data. Now, can you guess what value it would be between the range of -1 to 1? I can hear some of you say 0.9, 0.8, 0.95, 0.6. Let's see who is the winner. 0.95 is the winner. Yes, and because this is positive and it's almost close to 1, meaning that, and so we have that R, which is the correlation coefficient, is equals to 1. What about this? First, what would you say about the sign? Because with correlation, there are two things we are measuring. We are measuring the strength of the correlation of the relationship, and we are also measuring the direction of the relationship. So first with these, you can see that it's negative. So R would be equals to minus something. So you might guess maybe minus 0.75 or minus 0.80 and so on. However, when we did this in Minitab, based on this data, it is negative 0.8. So that's the correlation coefficient. What about this? What is the correlation? What's the correlation coefficient value of these scatter plots? Looking at these scatter plots, we can see clearly that there's no linear relationship. This seems to be curvilinear, and as such, the correlation coefficient will be equal to 0. So R here is equal to 0. What about this? The same way here as well, there's clearly no linear relationship between these two variables, so this will also be equal to 0. All right. So I believe now that with these, you have an idea of how these correlation coefficient is computed. So if there's no linear relationship, the correlation will be equals to 0. Okay, so let's look at this, the initial data. The correlation coefficient of these two variables is equals to 0.91. So we can interpret that it has a positively strong linear relationship. So there's a positively strong linear relationship between the variables number of crew and number of passengers. Great. Now, how do we compute the correlation coefficient? Here is the equation, my friends. In this class, as I said earlier, you would never have to really use the equation because you can simply use a statistical software like Minitab to solve for R. So I'm just putting this there for you to see what the equation is on how to compute R. But for this class, we'll use Minitab. And in the next video, I would show you, I would demonstrate how to compute the correlation between two quantitative variables using Minitab. So don't bother about the equation, but at least you can see what it looks like. Great. So there is a rule of thumb in interpreting the correlations. Like we said, the correlation value is between negative 1 and 1. Now assume that we have everything just positive between 0 and 1. How do we interpret this? So if the correlation magnitude is between 0 to 0.2, so if R is between 0 to 0.2, it implies that we have a very weak linear relationship. If R is between 0.8 and 1, it means that it implies an extremely strong positive linear relationship. That's how to interpret the correlation coefficients. So this is a rule of thumb. Great. Now, there is a famous data set called the Anscombe data set. It's an interesting data set in which, as you're going to see, so these 4 data sets all have the same correlation coefficient of 0.816. Look at this. Which of this scatter plot would really make sense for us to use? So looking at these, if you don't look at the data, you could simply just say, oh, the correlation coefficient is 0.816, so there's a strong positive linear relationship. Do not do that. A picture is worth 1,000 data points. It's important for us to visualize our data in order to derive insight from the visualization. Now, of all of these, I would say this one is what is okay. So I can clearly have what I call a football shape. here we're not talking about bell-shaped curve. So you have a football shape around this data. So that would be a good relationship. However, in these, it's clearly curvilinear. We can't really fit in a football around the data. And looking at these, there's clearly what we call an outlier. As you can see, this outlier is what influences the value of this of the relationship. And by visualizing, maybe this data was based on human error, and this is maybe meant to be somewhere around here. And that's why we have to investigate our data after visualizing. And here again, perhaps this was an outlier. This is clearly an outlier, but perhaps this was inputted based on error, and it's meant to be somewhere here. In that case, the correlation coefficient would not be 0.81 if we move this data point to this point. So this is just going to be a line here. So correlation, as we said, does not imply causation. That's pretty much the whole concept of correlation. In the textbook, there is a data set which I would also provide to you on Blackboard, the Midwest data set. In this data set, one of the things you can explore is the relationship between sales and years in Midwest. Now, here is a snapshot of the data. So we have sales in one column and years with Midwest. The research question is there a relationship between sales and years with Midwestern? So that is the research question. And with these, we want to first start by exploring the data by looking at the relationship between the two variables by creating a scatter plot. Here is the scatter plot, which was done in Minitab. So the relationship between sales and years with Midwestern appears to be positive and definitely linear. So you have a positively strong linear relationship. So the company is studying the relationship between sales on which commissions are paid and number of years a salesperson is with the company. Now, a random sample of 12 sales representatives was collected, and I would show you in a different video is how to compute the correlation coefficient in Minitab. So that's what we're going to do next. So how do we determine R? So what is R? If we're doing this by hand with the expression I showed you previously, then we're going to have a correlation coefficient of 0.8325. Please don't do this for your in this class. Just simply use Minitab, and it will give you the answer as you would see next. All right. So in Minitab, if you go to if you're using a PC statistics, then you see correlation, and I would show you next, no problem. All right, so now we've computed R, and we see, okay, there's a strong linear relationship between the two variables. Now the next question would be, is this significant? So how do we check if this relationship is significant or not? So in a population, we use the symbol rho. So this symbol rho, don't worry, this will be one of the last symbols we're going to look at in this course, rho. So RHO, to specify the population correlation coefficients. Okay, so we use rho to specify the population correlation coefficient. Now, if conducting a test by hand, a t-test statistic with a degree of freedom of n-2 is computed. So our test statistic is this. So for your homework assignment, you need to compute the test statistic for the correlation, and all you need is a correlation coefficient, which you would compute in Minitab, and you also need n, which is the sample size, or let's say n minus 2, which is the degree of freedom. So the degree of freedom. And you enter it into this equation. This is only the only equation that you're going to compute in this course. And if you create a function in Minitab to compute this based on R, so you're just going to input R and N, you can automate the process. Or you can do the same using Excel, so that in the exam, you simply just input R and N, and it gives you the value of the test statistics. That you can automate ahead of time, or for your homework assignments, I'm going to say as well. Anyways, so when we compute T, we are then going to check if it's usual or unusual to determine if it's significant or not. Now, like I said again, I'll repeat, in this course, you will never need to compute R or the test statistics, but you only need to compute the test statistics by hand, but not R. So you can use R, you can compute R from using Minitab. If I give you the two data sets, however, I will also show you how to determine T using Minitab without you having to use a calculator as well. So so it depends on what is given in the question. If in the question that I gave you what is R and I gave you N for a particular problem, then you will need to use this equation. So in order to use Pearson R, both variables must be quantitative, and the relationship between the two variables, which I'll call, say, X, and this is Y, and this is X. So the relationship must be linear. We should have a sort of a linear relationship. It could be positive or negative. So that we checked using a scatter plot. So this is a scatter plot. So the relationship, again, is linear in nature. Our null hypothesis states that there is no correlation, and our alternative hypothesis states that a correlation exists. You have all learned how to conduct hypothesis testing in the previous chapter, so you would understand how to interpret a two-tailed test. So with these, remember that we determine type of test based off the alternative hypothesis. And because we have a not equals to sign here, it means that this is going to be a two-tailed test. So we're going to have a rejection region at both tails as well to determine if it's significant or not. So your research question would be, is the relationship in the population different from 0? So that is how you can phrase the research question. Is the correlation in the population positive? Is the correlation in the population negative? That would be the research question. Now, for this example of the Midwestern, we can see that that T is 4.752. Now, to determine if it's significant, we would need to use the two-tailed test and compute the critical value of the T distribution. So this is a T distribution. And again, we had looked at how to create a T distribution how to interpret the T distribution in the previous chapter. Now, we will check. First, we have to determine what was alpha, what was the confidence level given in the question. Okay, it's not stated here, but we're using 0.05. And because we're using 0.05, this area is 0.025, this area is 0.025. So we set alpha to be 0.05. That you have to determine before you even conduct the test. You specify what the significance level is. And so based on these, we can clearly see that our test statistic is somewhere to the right. It's in the rejection region. So if the test statistic T is in the rejection region, then we're going to reject our null hypothesis. Okay? Or if it's towards the left as well, we're also going to reject our null hypothesis. But if it was in between, if t was less than 2.228 or greater than this, then we will fail to reject the null hypothesis. So because it's greater, we're going to reject the null hypothesis, and this is going to be our interpretation. Based on the sample evidence, we can conclude that there is a significant positive linear relationship between years in the company and sales volume. Sweet. Now you know how to interpret that and determine if the correlation, if the relationship is significant or not. So what have we covered so far? We have seen how to specify the population parameter of interest, formulate the appropriate null and alternative hypothesis, specify the level of significance, compute the correlation coefficient and the test statistic, construct the rejection region and decision rule, reach a conclusion, and draw a conclusion. Now we'll move on to the sister of correlation, which I call the simple linear regression. So regression analysis explores the relationship between a quantitative response variable and a predictor variable and one or more explanatory variable. So the response variable is the y variable and the explanatory variable is the x variable. Now there are so many terms that is being used, and for simplification for this class, the y variable, we'll call it the dependent variable, and the x variable, we'll call it the independent variable. And sometimes I might call it the predictor variable. So those are some terms I would use. So it is a statistical method that is used to describe the linear relationship between two variables in the form of a straight line. So that passes through the points of a scatter plot. And by simple, so simple is simple linear regression does not mean that it's a simple methodology, but it refers to the fact that we only have one independent variable or one predictor variable. When we have more than one predictor variables, then it's going to be a multiple linear regression. And that you're going to see in a different class. Okay. Now, if you are currently taking my Start 2 class, then that's what you're going to see next in the next chapter. All right. Cool. So when there are only two variables, a dependent variable and an independent variable, the technique is referred to as a simple regression analysis. When the relationship between dependent variable and the independent variable is linear, the technique is a simple linear regression. I'm still saying the same thing. Okay, so, all right. So these are the conditions that we want to meet before and to determine if our analysis is a simple linear regression analysis or not. Now, I have already talked about what a dependent variable is and an independent variable is. So let's look at an example. Is there a relationship between temperature and the number and the consumption of ice cream? That could be a business question that I could come up with in my company. So let's say I own a company where I make ice cream, and I want to see what drives sales. Is it that as the temperature increases, that the number of consumption of ice cream increases? So we can collect this data in order to analyze it. Now, we have this data of an ice cream data set, And what we saw is that as the temperature increases, the consumption of ice cream also increases in a particular community. So the question again here is there a strong evidence of a relationship between the independent variable and the dependent variable? So is there a strong evidence that there is a real effect? That's what we want to check. All right. So the true mean of y for a given value of x is equal to the line. So it's equal to the line. Now, if you look at this looks similar to the equation of a line where you have y is equals to mx plus c, but I know that you are seeing this, and then there's an error term that we're adding. So this y is referred to as the expectation of y given x. And here you're seeing some new terms, beta. These are called beta. Now, the beta terms are what we so it's called what we would use to test this relationship. So for example, beta 0 here is the intercept. Remember when we have equation of a line and the line goes this way, this point is the intercept between y and x. And then beta 1 here is the slope and x. So we have this as a slope change in y over change in x. So the change in y over change in x is beta 1, which is the slope. And then the e as the errors that we're going to compute between the data and the predicted line. So what errors are accommodated in this relationship? Okay, let's see. So yes, E is called the random error term. Good. So usually we see the equation of a line as this: y is equals to mx plus c. Some of you might say y is equals to mx plus a, but let's use y is equals to mx plus c. And here is an equation of a line. And so if we rearrange this equation, it will look something like this. So c is the intercept, and m is beta 0 is intercept, and beta 1 is the slope. Okay, so that's the relationship. So what we have here is an equation of a line, and we're going to test this beta term to see if this beta term is equals to 0. Now take for example, if beta 1 is equals to 0, it means that this term will become 0, it's cut off, and basically our y will be equals to the intercept, so the average of basically that will be the average of y. So there are different linear regression assumptions which we must take into consideration. So the random errors are statistically independent. For each value of x, there can exist many possible values of y, and the distributions of y values is normally distributed. The distributions of errors have equal variances for all possible levels, and a straight line called the population regression model will pass through the mean of the possible y values for all values of x. All right. Well, because this is really an introduction, I just want to state here that there are different assumptions we must take into consideration, such as linearity assumption, which is that the relationship between x and y must be linear. Okay, we can check that using a scatter plot. We also need to check independence of error. Independence of errors. So what that does here is that, so there is not a relationship between the residuals and the predicted values. So we need to check this assumption by examining a scatter plot of the residuals versus the fits. Then the correlation should be approximately zero. So the correlation should be approximately zero. And one other assumption is the normality of errors. So the normality of errors, and then we also have the equal variances, as I mentioned. So the equal variances is the variance of the residuals should be consistent across all predicted values. So we check this by examining the scatter plot of residuals versus fits. Now, the variance of the residuals should be consistent across the x-axis. Now, if the plot shows a pattern, so let's say, so the variance should be consistent. Now, if the plot shows a pattern, so take for example, something like this, or like a bow tie. So this is a pattern or a megaphone shape. Then variances are not consistent, and this assumption has not been met. I will show you how to do this in Minitab in the next video. So in the next video, I'll show you how to look at these assumptions in Minitab. Yeah. So estimates of a regression coefficient. So we have that the predicted y is equals to b0 plus b1 times x. Now, since we are dealing with our population equation is y is equals to beta 0 plus beta 1 times x plus the error term. Now, when we are going to do our analysis, we want to estimate the population from a sample. So B0 and B1 is gotten from the sample data, not from the population data. So these are the statistics from the sample. So y hat is the estimated value of the dependent variable for a given value of x. B1 is the true population regression slope coefficient. So is the estimate of the true population. By estimate means it's something we got from a sample. And B0 is the estimate of the true population y-intercept. Now, how do we determine the values of B0 and B1? Again, you can just simply use Minitab. So I decided I would just create a simple video titled Minitab for regression. So it's easy for you to just watch that video and rather than watch a lengthy video and trying to find where I brought in Minitab in the video. Okay. So we'll do that in Minitab, and you'll see how to determine B0 and B1. So for estimating the intercept and slope. So for least squares regression, we want to estimate beta 0, the intercept of a line, and beta 1, the slope of a line, is what we want to estimate. Now, before using a statistical software, the question is that, do we estimate this by trial and error? So let's look at these scatter plots. Given the scatter plot that examines the relationship between temperature and the consumption of ice cream, let's let's determine which regression line is best. Okay, so we can do this by examining the errors. So let's say I had a line here. If I say this is my line, then I can compute all the errors. So this is the predicted line, and this is the original data. So the difference here is the errors, what we call the residuals. All right, so looking at this, let's say we fit a line like in this direction. My question is, would this be the best fit? Would this be a good line? I'm sure your answer is as good as mine, which is no. The points are far from the line. So this would give a high regression error. What about this? Is this a good line? No. The points are far from the data. So you have some data up here and there's nothing around here, and you have some data around here, which is pretty far. So the points are far from the line. What about this? Is this a good line? Yes, because I gave you the way in the beginning. I drew a line that was similar to this. So yes, in this case, we would have a lower regression error. Our objective function would be to minimize our regression error or residuals, known as the sum of squared prediction. So this difference here is our residuals, and residuals. And what we did by trial and error is known as the least squares criterion. Least squares criterion. So what we're trying to do was find the line that best fits this data. So it is the criterion for determining a regression line that minimizes the sum of squared prediction errors, or that minimizes the residuals. Looking at this, how do we compute the residuals from different points? Well, just to put this in context, the residual is the difference between the actual value and of the dependent variable and the value predicted by the regression line. So take an example here. The actual value is about 312, and the value predicted by the regression line is somewhere around here, which is about 390. So the residual is this difference. And so the difference here is negative 78. So we compute all these residuals and then find the sum of squared difference. And I'm going to show you next. So, and again, in this course, you will be responsible for computing predicted values and residuals by hand. You will not be responsible for computing the intercept or slope by hand. We will do that using Minitab. Now, let's say we fit a line horizontally and we want to find the sum of squared residuals. So first here we have the predicted y values, and here we have the actual values, and here we compute the residuals for each of those points, and these are our residuals, and we found the sum of squared difference, and this is the value we have. All right, so this is 301,000, and we tried another line and we saw that this is now 102,000. So we can see that this line is a much better line than this, because our sum of squared residual is much smaller here. However, can we have a better line that fits this data better, that gives us a much lower sum of squared residuals? Yes. So looking at this is much lower than the previous line. So we can now see that we have reached our optimal point, and we have found the line of best fit. Great. All right, so we will not do this by trial and error. We would use several statistical software, and for this class, we're going to use Minitab. You can also compute this in Excel, in SAS, in R, and so on. So what's the least squares criterion? So residuals are symbolized by the epsilon, which you saw earlier, in a population, and we use E in a sample, okay? So as with most predictions, you expect there can be some error. So for example, if we are using height to predict weight, so if we're using height to predict weight, so we have height is in the X variable to predict weight. And that's the dependent variable. We wouldn't expect to be able to perfectly predict every individual weight using their height. So there are many variables that impact a person's weight, and height is just one of those many variables. So these errors in regression predictions are called prediction error or residuals. So they're called prediction errors or residuals. So a residual is calculated by taking an individual observed y value minus their corresponding predicted value. And so this gives us the residual E. Okay. So therefore, each individual has a residual. So the goal in least squares regression is to construct the regression line that minimizes the squared residuals, That's the goal. So in essence, we create a best fit line that has the least amount of error. That's our objective. So what does the squares in the method of least squares refer to? What does the squares refer to? So the squares of vertical differences between the observed point and the regression line. So the least squares, to compute V1, the slope and the intercept, this is the expression. We will use Minitab to compute this. Don't bother about this equation, but it's just put for you to see what it looks like. Minitab, we will use Minitab. So statistical software will compute the values of y-intercept and the slope that minimizes the sum of squared residuals. The conceptual formulas here show how these statistics are related to one another and how they relate to correlation, which you learned earlier. Now, again, we will use Minitab in the next video to compute B1 and B2. Cool. All right. Again, here I'm showing you how to compute B1 and B2, how to interpret these equation. I'll just skip forward and just show you that, okay, B1 is equals to these, and this is B0. Sweet. Now, in Minitab, you can create the scatter plots and look at the linear relationship. And using Minitab, you would also determine what the equation is. So with Minitab, you will determine that, okay, this is the intercept and this is the slope. So this was done in Minitab, and this is a typical Minitab output. And from this output, we can see here that this is the intercept and this is the slope. So this is B0 and this is B1. So stay tuned for the next video where I demonstrate these concepts in using Minitab. All right. Now, next, we can use statistical inference, that is hypothesis testing, to draw conclusions about how the population of Y values relates to the population of X values based on the sample of X and Y values. Now, so here's the hypothesis. So we say that our null hypothesis is that beta 1 is equals to 0, and the alternative is that beta 1 is not equals to 0. So the slope of 0 would imply that there is no linear relationship between X and Y variables, and that the X variable in its linear form is of no use in explaining the variation in Y. So if B1 is equals to 0, basically our predicted value of Y is simply the average, and which is the average of Y, which is the intercept. So what? Great. Okay. So remember, we mentioned that the assumptions of simple linear regression are linearity, independence of error, normality of errors, and equal error variance. Whenever you're conducting any regression analysis, you should check all of these assumptions before you proceed in interpreting the result or coming up with a conclusion. So this is the general form of the hypothesis for the regression equation, simple linear regression equation. We only have one beta 1. Now, if it's multiple, you have beta 1, beta 2, beta 3, depending on the number of independent variables. Here we have just one independent variable. How would we describe the research question based on this hypothesis? So we could say that, is the slope of the population different from 0? So that is how we can formulate the research question. Now, looking at this, we know that this is going to be a two-tailed test because we have a not equals to sign here. So we're conducting a two-tailed test. And so it's non-directional. And so next with these, we would compute the test statistic, and I will do this again using Minitab to compute the t-test statistic. And for that, we need to know the degree of freedom, which is n-2. And it's n-2 because we have to factor two variables here in question. And that's why it's n-2. So B1 is a sample regression slope coefficient. Beta 1 is the hypothesized slope. This is how to compute the test statistic, but you would not. I will show you again. I keep saying this in Minitab. All right, let's move on. But you can see how this is similar to what we did in chapter 9. In chapter 9, the test statistics is similar to this. So this is the standard error, and so this is so remember we have something like x bar minus mu divided by sigma of x bar. So it follows the same concept in determining the test statistic. So it's like looking at the sampling error. And so this is kind of the sampling error for the beta term over the standard error. So again, this is the estimator of the standard error of the slope. That's the SP. And that's how to compute XP. So, and I will show you how to determine the standard error in Minitab, how to interpret the output of a regression analysis using Minitab. So here is a typical output in Minitab, and the question is, what is the standard error? So the standard error is shown here. That is what I have circled. So when you run your regression analysis for the sales versus years with Midwest, this is the output you're going to get. So if you're trying to determine what the standard error of the slope is, you have the symbol S here, and that is this value. So rather than compute all of this, compute this by hand, you simply derive the answer from the results in Minitab. Okay. So SE is called the standard error of the estimates. And what is this? This is the standard error of slope coefficients. So for each of the slope, so this is the slope, yes, with Midwest. This is the standard error of the slope coefficients. And this is the t value, the test statistics for the slope. Remember, we computed the test statistics for the slope to check if this variable was significant or not. And we got something about 4.75 by hand. So this is the test statistic. So basically, you're going to use this value and compare it with the critical value, or you compare the p-value with the significant value of alpha. So if the p-value is less than alpha, then you're going to reject the null hypothesis. Or if the test statistic is greater than the critical value, which means that our test statistic is in the rejection region, then we are also going to reject the null hypothesis. Okay, you get what I'm saying? Cool. So the test statistic is computed this way. Again, that's the test statistic. So testing whether the slope is statistically significant. And by looking at the results, this is the value. So don't do this by hand, as I've shown in the slide. Just simply do this using Minitab, and you get your answers easily. If you're doing this by hand, then that will be the answer. All right. So you saw how to determine the critical values in the last class in Minitab. I showed you in a previous video. Now from a t-distributions. So looking at these distributions, so we have alpha is 0.05. This is clearly the rejection region. Now, and our critical value is this value. Now, if our test statistic is 4.752, what will be the decision? So our decision would be that if our test statistic is greater than this value, we would reject the null hypothesis. Or if it's less than this value, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So with what we have done so far, because our test statistic is greater than the critical value, we reject the null hypothesis and conclude that the true slope is not 0. So that means that the simple linear regression relationship that utilizes the independent variable years with the company is useful in explaining the variation in the dependent variable sales volume. Now, some common critical values, some common Confidence level was what we saw in the previous chapter. We can have 0.9, 0.95, 0.99. So if it's the confidence level, you know how to compute what the alpha value would be. It should be 1 minus the confidence level. But the most commonly used confidence level is 0.95, which is alpha of 0.05. One question we could ask ourselves is, why is the normal approximation useful for linear regression? Because here again, we're using the normal approximation in driving our conclusion. So why is it useful for linear regression? So it tells us more about the y values. So from regression, we know for a specific x, and the normal approximation tells us more about the actual values of a specific x value and how they look like. So as they follow a normal curve. So that's what it really shows us. Great. Again, you can come up with your conclusions using the p-value. So here you can find the p-value. And if the p-value is less than alpha over 2, since it's a two-tailed test, we would reject the null hypothesis. Okay. So you can either make your decision using the p-value or you approach, or using the critical value to compare with the test statistic. And then you can draw your conclusions, your interpretations in terms of the original research question. Okay. So how do we interpret the sums of squares? In the output, you'll see things like the total sum of square, you have the sum of squares regression, and I would point to you where those values are, and the standard error of the estimate, which is the SSE we've seen earlier. So the total sum of square is equals to the sum of squares regression plus the sum of squares error. The sum of squares regression is basically the sum of squares of the whole model. Now looking here, the sum of squares regression can be seen from this value, computed from this value. The sum of squares error is computed from this value, or it's this value. And the sum of squares total is basically the sum of is this value. So remember that the sum of squares total is equal to the sum of squares regression plus the sum of squares error. And when you add this and this, it gives us that. Rather than trying to do this by hand, you just simply need to know how to interpret the results from a regression analysis, from a simple linear regression in Minitab. Great. Good. And finally, before we end this video, let's talk about R. How do we determine the goodness of fit? So we determine that using what is called the coefficient of determination, R squared. So the portion of the total variation in the dependent variable that is explained by its relationship with the independent variable. Now, R squared is simply the sum of squared regression divided by the sum of squared total. You don't really need to do this because you would find the R squared in the outputs in Minitab. But I'm just putting this in case I give you a table where you have SSR and SST, and I ask you to find R squared, you have to it's SSR divided by SST. Okay, so R squared is the correlation the correlation coefficient squared, the squared of the correlation coefficient. That is R squared, and R squared measures the goodness of fits. So big R squared is equals to R squared. Okay. One more. Yeah, that was not the end. Great. So looking at this output, our R squared is basically 69.31. So that's R squared. So R squared is, you can say it's 0.6931, which tells us that 69.31% of the variance of the variance in sales can be explained by the years with Midwest. So this is fairly good R squared for a simple linear regression. Well, the higher the R squared, the higher the goodness of fit, basically. So we don't want it to be less than 70 plus or minus a smaller difference. So 69 can be said to be a fairly good R squared. Again, R squared, if you divide this, you're going to get the same outputs or the same results. All right. So the regression equation indicates that for every, also one of the outputs you get in Minitab is the regression equation. So it explains that for every increase with Midwest, the sales will increase by $49.9. That's how we can interpret this. So for every year increase with Midwest, the sales will increase by $49.9. If this was negative, then the sales would decrease. But since we have a positive slope, the sales will increase. So the slope of the regression line tells us if it's going to be increase or decrease. Okay. So you get the picture. So that's it. Let me clean this off. Yeah. Finally, the fitted line plot shows us the regression equation of the scatter plot. Now, yes, you have yes with Midwest, we're trying to use yes with Midwest to predict sales. And here is our fitted line, our regression equation. As we said, for every year, 1 year increase with Midwest, sales increases by 49.91. So in this video, you have learned how to test for statistical significance of Pearson's R. So this R is called Pearson's R, and the slope of the simple linear regression line using the T distribution to approximate the sampling distribution. I also introduced you to the coefficient of determination, which is R squared. So I think this is a good point to end this video. With this, you have a good understanding of correlation. You also have a good understanding of a simple linear regression and how to interpret the results of a simple linear regression as well. So, are there any questions? Well, I have some questions for you. What is a residual? If you're following me, you should be able to answer that. If you said any point below the regression line, So if you have this line and this is this, and you have this line up here, so that would be our residual. This is the residual. This is the residual. So it is the vertical distance between a data point and the regression line. So this is the regression line. So this vertical distance is the residual. Great. What other questions do you have? Now remember, if you have any question, you know how to get in touch with me. So reach out to me and I'm happy to answer your questions. And so with these, I wish you all a beautiful rest of your day, depending on what time you're watching this. If it's at night, I wish you a good night rest and all the very best. Stay well, stay healthy, and stay blessed. Stop video.